Hey everyone. So the last bit of our derivatives unit is going to focus on applications. And the first sort of set of word problems that we're going to look at is position, velocity, and acceleration problems. Then we're going to move into related rates after this, and we'll spend a couple days on related rates. Okay, so we've actually already dealt a little bit with position and velocity. You know that a position function is that s of t, right? And it describes an object's position over time. Then we took the derivative of the position function, and that was the velocity function. Okay, so that would describe the object's instantaneous velocity over time t. The one thing we're going to add into this conversation now is the second derivative. So the derivative of the velocity function is acceleration. Okay. Okay, so we have seen that if the position or distance or displacement function, those all mean the same thing, is defined as s of t, then the velocity function is the derivative of s of t. Today, we're going to introduce the concept of acceleration. Acceleration is defined as the rate of change of the velocity. So remember, as soon as you see the rate of change, that's the derivative, right? Because that's looking for the slope of each tangent line. That's what's going to give you the rate of change along the function. So the rate of change of velocity is acceleration. So it's the rate of change of velocity of an object with respect to time. So velocity, v of t, is the derivative of s of t, and acceleration, a of t, is the derivative of v of t, also known as the second derivative of your original function. So s prime prime of t there, okay? Okay, so an object is moving in a path described by s of t equals t squared minus 4t plus 8, where t is greater than 0, s is in meters, and t is in seconds. Okay, determine s of 12. Well, that's fairly easy. I've already got my s of t function. My input is 12. I just plug in 12 and get out an answer. Okay, and I get 104. So s of 12 is 104 meters. Now, determine the velocity after 12 seconds. Well, to get the velocity after 12 seconds, I need the velocity function, which is the derivative of s of t. So I'm going to take the derivative of s of t. I'm just going to hide myself for a second just so you can see this equation again. I'm taking the derivative of that, so that's going to be 2t minus 4. Okay, 2t minus 4. So then I plug 12 seconds, that's my time value. I plug that in for t in the velocity. So 2 times 12 minus 4, I get 20 meters per second. The units are really important in these questions. Make sure you're answering with the proper units, and you'll always figure out the units based on what the units were in the question, okay? Then we want when the object is at rest. Well, when the object is at rest, I have a velocity of 0, right? I'm not moving. So I take my velocity function, which is 2t minus 4, and I just set it equal to 0 and solve for t. Okay, so that gives me oops, sorry, I didn't mean to go that far. Let me just go back for a second. That gives me 2 seconds at 2 seconds, at the time interval of 2 seconds, the object will be at rest, okay? Why an object is at rest? Could be that it stopped. More often, it's that it's right at that instant changing direction, okay? Okay, so given h of t is t cubed minus 3t squared minus 5t, where h is in meters and t is in seconds. Determine the velocity at 2 seconds and at 4 seconds. Well, in order to determine the velocity, I need the velocity function, which will be the derivative, in this case, of h of t. So the derivative of that will be 3t squared minus 6t minus 5. Okay, and so now I just plug in 2 and I plug in 4. So if I plug in 2 for t into my velocity function, I'm going to get out negative 5 meters per second. Okay. And then if I plug in So that we're moving in a negative direction there. That's what that -5 is referring to. If you have a negative velocity, you're moving in a negative direction. Okay. And then if I plug in 4, I end up with 19 meters per second. So that would be going in a positive direction. Okay. So a negative refers to movement in a negative direction, and a positive number refers to movement in a positive direction. Okay. Given S of t is 2t cubed minus 21t squared plus 60t, where t is greater than 0, s is in meters, and t is in seconds. When is the object at rest? So in order for the object to be at rest, I need a velocity of 0. I need, first of all, the derivative function. So I need b of t. So that's going to be, the 3 will come over, so that'll be 6t squared minus 42t plus 60. Okay, now I'm going to set that equal to 0 if I want the object at rest. I can also divide all of that by 6. That'll just make my life a little easier. Okay, so then I'm going to factor that. That's going to go into t minus 2 and t minus 5, which means t could be 2 seconds or 5 seconds. So at 2 seconds and at 5 seconds, the object is at rest. Okay, 2 seconds and 5 seconds. Okay, the next question is, determine when the object is moving in a positive direction. Well, I need to take those moments where I'm at rest. I just said in the previous question that it's when we reach a velocity of 0, 9 times out of 10, that's where I'm changing direction, right? So what I need to do is, essentially, this is going to be very similar to 20-1, when you were trying to figure out algebraically when something was greater than, when a quadratic was greater than 0 or less than 0. You did a algebraic process called roots and powers. This is essentially, or roots and test points, sorry, roots and test points. This is essentially the same thing. What we're going to do is we're going to take those two sort of guideposts, those 2 points where the velocity is 0, and we're going to test on either side of them. Okay, so I know this graph only starts at 0, so I'm on a number line. I'm thinking of like 0 to 2, and 2 to 5, and 5 to infinity. Okay, so essentially I'm looking at t squared minus 7t plus 10 is greater than or equal to 0. I've already factored that. I know it's -5 or 5 and 2 for my t values. So what I do is I plot that. So this section right here just represents less than 2, but in this case, it would represent 0 to 2 because the graph only starts at 0. This section here would represent 2 to 5, and this section here would represent greater than 5. So what I want to do is I just want to plug in a nice friendly number that's easy to work with. For instance, like maybe here I want to just plug in 0 and see. Okay, if I plugged in 0, I get 10 is greater than 0. If I plug 0 in for there. Yeah, is that a true statement? Yes, it is. So that's true. If I plug a number in between 2 and 5, so let's say 3, I get 9 minus 21 plus 10. That is a negative number. So that is not greater than 0. And then maybe I'll plug in something friendly above 5. So let's plug in 10. I get 100 minus 70 plus 10. That would be a positive number, so that works. Okay, and so when I test each of these areas, I get it working when it's less than 2, not working in between 2 and 5, and working when it's greater than 5. Okay, so the check marks, these are when the object is moving in a positive direction. Okay, so between 2 and 5, it's moving in a negative direction. Okay, so my answer would be from 0 to 2. Remember, my graph only starts at 0. That's why I have to start at 0 on my answer. Okay, so 0 to 2 in union with 5 to infinity. Okay, 0 to 2 in union with 5 to infinity. Okay, what is the total distance that the object has moved in 5 seconds? You can't just place 5 in for t here, because if you just place 5 in for t, you're getting the movement at 5 seconds. You're getting the displacement at 5 seconds. but that's not the total displacement because you've changed direction, right? And so what you have to do, you can now foresee kind of 3 different chunks of this graph. You can foresee that I'm moving in a positive direction from 0 to 2, and then I'm moving in a negative direction from 2 to 5, and then I'm moving in a positive direction from 5 and beyond, okay? So what I wanna do is I need to figure out each of those sections. So I need to know where I am at 0, where I am at 2, and where I am at 5. Okay, so because the object is changing directions, we need to add up the distance from the individual components. Okay, so S of 0 is 0, S of 2 is 52, and S of 5 is 25. So what I need you to see then is from 0 to 2, I moved from 0 to 52, so that's a total of 52. Okay, but then from 2 to 5, I moved a total of 52 minus 25, right? So that would be what, 27? Okay, so I moved 52 in the first section and 27 in the second section. So then I have to add that up. Okay, so essentially this is what I did. I said the distance is S of 2 minus S of 0. That's what I just did in the conversation, right? Don't let the equation freak you out. This is literally the conversation we just had. And then I'm going to add to that S of 5 minus S of 2. And I do the absolute value because it doesn't matter right now whether the direction was positive or negative. I'm only looking at the distance itself. So even if I'm moving in a negative direction, I still want to include that not as a negative here because I'm looking for the total distance. Okay. And then so that gives me 77 or 79, sorry. My math was a little off. So 52 minus 0 is 52. And 25 minus 52 is 27. So last I looked, 52 and 27 is 79. Don't know where the 77 came from, sorry. Okay. All right. Awesome. So if then determine the acceleration of the object at 4 seconds. Okay, so I know my velocity function is 6t squared minus 4t plus 60. Acceleration is now going to be the derivative of the velocity, or the second derivative of the position function, okay? So the derivative of the velocity, I'm just going to get myself away there so that I'm not hiding the v of t. So if I took the derivative of this, that would be 12t minus 42, okay? So 12t minus 42, and then all I've done, because it's at 4 seconds, I just plug in 4. So I get 48 minus 42, so 6 meters per second squared. The acceleration at 4 seconds is 6 meters per second squared. Okay. All right, and then just for your own kind of benefit, what I've done is I've graphed all 3 of these functions. So the blue is my original position function. The green is my velocity function. And the pink is my acceleration function, okay? So if I followed the blue up for a second, I want you to notice that as I change direction here, that's where my velocity is 0, right? So my velocity is going from a positive direction to a negative, sorry, a positive value to a negative value, okay? Because I'm moving from a positive direction to a negative direction. Okay. And then I have another change here. So right at the change here, my velocity becomes 0 again as well. And then when my velocity changes from being positive to negative, a positive direction to a negative direction, my acceleration was 0. Okay. So everything fits with our knowledge of derivatives. Okay. So your job is now to head over here, and next lesson we're going to talk about related rates. Okay, so I'll see you there. Take care.